Bismillahirrahmanirrahim. Dear students, we are talking about the chapter number 4 for the grade 11. Today the lecture is 38, gases chapter, first year class, van der Waals equation. So in the van der Waals equation, there are two correction factors. One is a correction factors to the ideal gas equation. So one is a volume correction and other is a pressure correction. Last time I told you the non-ideal behavior of the gases. How the gases behave, non-ideal behavior. So there are two faulty points in the kinetic molecular theory of gases. There are two faulty points in the kinetic molecular theory of gases. There are no attractive or repulsive forces present between the gas molecules. The volume of gas molecule is negligible as compared to the volume of the container. So these 2 points are faulty in the kinetic molecular theory of gases when pressure is very high and temperature is very low. At very high temperature and low temperature, these 2 points are invalid. So there is no validity for these 2 points. That's why the gases show non-ideal behavior. Gases show non-ideal behavior. So that's why this graph I told you, which have a 2 box, which one is a purple color and other the yellow color there is. And I told you there is one more which shows a straight line, which give a borderline between the 2 colors. So if that is straight line to the pressure, then we can say the gas is ideal. But no one gas is ideal. But if you see the gases which are very lighter gases, they show somehow ideal behavior. So number of moles P is equal to nRT. Show the straight line if the gas is 100% ideal. This is called a compressibility factor. For the ideal gas it should be a 1, whereas for the real gases it is not a 1. That's why the gases which are very polar, they go down, they give more non-ideal behavior, and in the yellow boxes, these are the gases, hydrogen and helium. So these gases somehow show the ideal behavior. Now the van der Waals correct the 2 factors, volume correction and pressure correction. The general gas equation, which is called P is equal to nRT, which is ideal gas equation, which is not applicable for the real gases, non-ideal gases at all temperature and pressure. So in order to make applicable to real gases, Dutch scientist van der Waals in 1873. In 1873, a Dutch scientist van der Waals made correction in volume and pressure. Correction in volume and pressure. He made correction in volume and pressure to make the gas applicable for the real gases. This equation is called a van der Waals equation. So we have to derive the van der Waals equation according to these 2 factors. One is called volume correction and another is called a pressure correction. So number 1 is a volume correction. Volume correction. So van der Waals thought that the sum of the volume of the vessel is occupied by the molecule of gas and the volume is not available for the free movement of the molecules. According to kinetic molecular theory of gases, you've done that all the gases, they go straight line, they move straight line unless they collide with each other and with the wall of container, their direction is going to be changed and they exert pressure, and these collision of the gases are perfectly elastic. So same he is saying that van der Waals thought that the sum of the volume of vessel is occupied by the molecule of gas. There is a vessel container, the volume occupied by the gas molecule, and that volume is not available for the free movement of the gas molecules. Actually, here we need the free volume of the gas, and it's obtained by when the subtract individual volume of the gas, individual gas A, gas B, gas C, individual gas volume from the volume of the vessel whole. So here the equation is given in your book that this V is a free volume. Mr. V is a free volume of the gas, and this V is a volume of vessel container minus the volume is of the molecules. Free volume is equal to vessel of the volume and the minus volume of the molecules of the gas. So volume of the molecules may be written here N B, where N is the total number of moles, total number of moles and B is the constant individual volume of 1 mole of the gas, individual volume of gas. So V is equal to NB. That's why if you write here, so V free will be is equal to volume of vessel minus MV. So please remember this equation we will put to get the van der Waals equation. So this is called a volume correction. Again I am telling you the volume correction is van der Waals thought that sum of volume of the vessel is occupied by the molecule of gas and that volume is not available for the free movement of the molecules. Actually we need a free volume of the gas which is obtained by subtract individual volume of the gas, means volume of the vessel minus volume of the molecules of gas will be equal to free volume. So molecules of gas will be equal to NB, where N is the number of moles of the gas and B is an individual volume of 1 mole of the gas. So when we insert this is the free vessel volume, molecular volume, V this molecules will be equal to N total number of moles and B is the individual volume of 1 mole of the gas. So if you put here, you will get a free volume is equal to volume of vessel minus NB. So this is the one equation, and we have to put and get the van der Waals equation. So this is called a volume correction. Volume correction. Write down this. Number two is a pressure correction. Pressure correction. So dear students, in the pressure correction, I told you that when the gas mixture or one gas is present in the closed container, so it going to move in the straight direction. The direction is only changed when it strikes with the wall of container and with each other, and it exerts pressure. And these collisions are perfectly elastic. The pressure which is exerted on the wall of vessel is due to the collision of the gas molecules. Already I told you, more the collision, more the pressure exerted by the gas. Since there are some weak force of attraction among the gas molecules, weak force of attraction, so the molecules of the gas cannot hit the wall of vessel with that much force with which they should have in absence of these attractive forces. I am repeating again this. Since there are some weak forces of attraction among the gas molecules, so the molecules cannot hit the wall of vessel with that much force with which they should have been in the absence of these attractive forces. It means that pressure being observed on the wall of the vessel is a little bit lesser than that of the ideal pressure. So that's why here the equation is pressure observed is equal to pressure ideal minus pressure less than. Pressure observed is called pressure ideal minus pressure less than. If the ideal pressure is denoted by I and less than pressure is denoted by P dash, then the pressure of ideal will be is equal to pressure observed minus pressure lessened. Due to the molecular attraction is denoted by P dash. But the P lessened is directly proportional to the density of the gas. Heavier gas, which is going to be more pressure created. So that is why P dash is directly proportional to the square of the density. Square of the density. P dash is directly proportional to the density of the gas, so P dash will be is equal to density is equal to mass per unit volume, and we have here number of moles. So we have number of moles here for the calculation, students. So that's why for the solving this one, so P dash will be is equal to, because we remove the proportionality sign, make equal sign, then put the constant. This is a constant A, which is called 100 volts constant, and then M square over V square. P dash is equal to A M square over V square, where M is a number of moles of gas, V is a volume, A is a proportionality constant, van der Waals constant. Proportionality constant or van der Waals constant. So now put the value here. Put the value here. Then you will get P ideal. P ideal will be is equal P dash plus, then this is the formula for this one, AN square over V square. AN square over V square. Pi is equal to P. Observe, if you want to remove this, put it for writing this one. Okay. So P ideal is equal to P plus AN square over V square because of P dash is equal to this factor. So if I put this in this equation, so you will get this one. Now we have another equation. We have another equation. So this is the P observed. This is the P pressure ideal. This is a P lessened. So P ideal is equal to P observed minus P dash. Pressure is directly proportional to the square of the density. Then P is equal to A, which is called proportionality constant, N square over S V square. So for the P dash, we have A N square. P is already present here. So A N square over V square. So you have another equation for this in the pressure correction. So we have two equations. One is called volume correction equation and other is called P correction equation. So I will write both. According to general gas equation, ideal gas equation, PV is equal to nRT. This is the general gas equation. Now, dear students, we have a volume correction equation here. Volume correction equation is V is equal to V vessel minus NB. This is the volume correction equation. And you have also pressure correction equation. This is the P ideal is equal to P plus A N square over V square. So dear students, we have two equations these. So if you insert these two equations in the van der Waals, so if you have a P, instead of P, you have to write P plus A N square over V square. For the V, you have a V minus N, V is equal to nRT. So you have this equation after inserting. If the number of moles are 1, keep constant 1, then you have a van der Waals equation P plus A over V square, V minus B is equal to RT. So this is the van der Waals equation. This is the van der Waals equation. A is a constant factor for the gas. Every gas has its own constant. On the next page, maybe the same page in the yellow box, you are seeing the values of A and B also constant factors, and A or B square volume B minus B is equal to RT. This is called a van der Waals equation. Now if you see your book, there is one thing, units of A constant and B constant. So dear students, if you have a P is equal to A n square over B, so will be A n square is equal to PV, or A will be is equal to PV over n square. So students, the units of A, B is a pressure, unit is atmosphere, V is a volume, unit is a decimeter cube, N is a number of moles, so per mole square. So that's why its units are decimeter cube, atmosphere, per mole square. Don't forget this. This is a value of A which are given here also. Square. E square. So decimeter 6. Decimeter, if you see the equation, they are the V square. Yes, they are the V square. So decimeter 6 atmosphere per mole square is the unit of A. V is an individual volume of the gas in 1 mole. Volume of the gas in 1 mole, that's why its unit will be decimeter cube per mole. Decimeter cube per mole. These are the units of the A and B. And if you see the table van der Waals constant for some gases, just like hydrogen has a 0.0247 decimeter cube atmosphere per mole square for the A constant, and for the B constant 0.0266 decimeter cube per mole. So you have a table, you can see these values are given here. In the numericals, these values are also given. So these numericals are very important. In exercise 2, numericals are given, and one is a salt here. So this is the van der Waals equation. P the pressure, A the constant, B volume, incompressible volume, R gas constant, T the temperature. So these are the constants. Constant will be given for every gases. You have to put, and what the examiner asks, you have to calculate accordingly. Sometimes he say calculate pressure, sometimes he say calculate the temperature. So all the values will be given. You have inside here calculate this factor, then calculate this factor, multiply then R value and P value. You have to able to calculate the pressure as well as temperature. So here is given the one example. One mole of methane gas. Example number 4.17. 1 mole of methane means N is equal to 1 for the gas is a CH4 methane. N is equal to 1. Maintain temperature. T is equal to 300 Kelvin. So volume V is equal 250 centimeter cube divided by 1000, you will get the decimeter cube, which will be equal to 0.250 decimeter cube. Okay. Calculate the pressure P. Calculate the pressure exerted by the gas under following conditions. Number one condition is when the gas is ideal. Number two, when the gas is non-ideal. And the value for the A for the methane gas are given in the book. 2.253 decimeter 6 atmosphere per mole square. For the value of B, which is volume, that is a 0.0428 decimeter cube per mole. So these are the values you have. So when the gas is ideal, so you have to use the formula PV is equal to nRT. This is called ideal gas equation, general gas equation. So for the ideal gas, calculate the pressure nRT divided by. So students, put the values here. And number of moles is 1 mole. R is the general gas equation, 0.0821. Temperature is a 300 Kelvin. Volume is a 0.250 decimeter cube Kelvin. And the units of the general gas equations are decimeter cube, atmosphere per mole per Kelvin. So by using these formulas, inserting the values with the units, you will get the answer 98.52 atmosphere. 98.52 atmosphere. So students, methane gas, which is non-polar, methane gas is non-polar, which must some have ideal behavior. But if you apply these conditions according to examiner, temperature this, pressure we have to calculate, volume this, number of moles this, A and B values are given according to these conditions. So pressure is very high, 98.52. The pressure is a high pressure. Dear students, it means that according to this condition, methane is non-ideal. Because non-ideality, two factors I told you, the gas is non-ideal at high pressure and low temperature. The pressure is very high. That's why if you are using the ideal gas equation according to these conditions, the methane gas is non-ideal. Now, when you use the van der Waals equation, when the gas is non-ideal, so van der Waals equation is P plus n square A over V square, V minus NB is equal to nRT. This is the non-ideal gas according to van der Waals derivation by using volume correction and P correction. Please, you have to calculate this pressure. M value is given, A value is given, volume is given, N is given, B value is given, N is given, R is given, and T is given. So dear students, if you calculate the values for the pressure according to the non-ideal behavior of the gas, so the answer comes 115.2652 atmosphere. 115. And when the gas is ideal, that is a 98.52. So if you take a difference of these two pressures, okay, no problem, then again you have a more pressure. This is the 115.2652 minus 98.52. Still you have a 16.745. Still the pressure is high. When you apply ideal gas equation, when you apply the non-ideal gas equation for the calculation of the pressure, so you have more than 16 atmospheric pressure by taking difference of these two pressures. Non-ideal gas pressure minus ideal gas pressure, you will get a difference. Still it comes more than 16. So we can conclude that by applying these two pressures, ideal gas equation pressure and non-ideal gas equation pressure, according to these values which are given, so gas is non-ideal. Gas is still non-ideal. So students, this is the gas equation. Now if you see the exercises questions I am giving you, you have to solve these two. If you see the exercises question, question number 16, by using van der Waals equation, find the temperature. Now here, this, find the temperature. R will be constant, N will be given, B constant, volume given, P given, all given. If you read very carefully, question number 16A, value of A given, B given, volume given, pressure given, number of moles given. So calculate temperature. This is temperature. So students, you have to calculate this one. Also there are many other derivation of general gas equation, derivation of the van der Waals equation. So already I derived here. Calculation of density, I told you the formula of density also. So students, these are numericals may be asked by calculating pressure and calculating temperature. This is the general gas equation. Now after that, there is another very important law. These terms are very important. There is one more very important law which is called Dalton's law of partial pressure. Dalton's law of partial pressure in a closed container. In a closed container, if we have gases, certain gases, this is a closed container, gas A, gas B, gas C. And there is a one very important condition you must write while writing the definition of Dalton's law of partial pressure. These gases should not react with each other. Non-reactive gases, hydrogen, oxygen, they don't react. Helium, neon, argon, nitrogen. Non-reactive gases, because we are talking about physical behavior of the gases. English chemist John Dalton, 1766 and 1844, exactly in 1801 he put forward the law that total pressure in the container exerted by the gaseous mixture, he said, is equal to sum of the partial pressure of each gas present in the mixture. It means that total pressure of the container, gas present in the container, total pressure must be equal to partial pressure of the gas A plus partial pressure of the gas B plus partial pressure of the gas C. Total pressure exerted by the mixture of gases, these gases must be non-reactive gases, is equal to sum of the partial pressure of gas present in a closed container, is called Dalton's law of partial pressure. So you have the example in the air. Nitrogen is a 78.08%, oxygen is a 20%, argon is a 0.93%, carbon dioxide gas 0.03. Now it is going to be increased by using pollution. 0.033 maybe is going to be increased. Million tons are going to be added. So this is very bad. So, and also you have the inert gases, helium, neon, krypton, and also hydrogen gas, and some also dust particles and water vapors. So these pressure is exerted by these gases is equal to sum of all these gases partial pressure to give a total pressure. And that we are exerting at sea level according to the calculation, according to the instruments, manometer, barometer, that is a 760 millimeters of mercury, 1 atmospheric pressure, or 760 torr, or 101325 Pascal, newtons per meter square also. So we are exerting this pressure. So this ratio should be maintained in the atmosphere. So students, this is called a Dalton's law of partial pressure. Now there are applications and relationship. Inshallah, next lecture I will continue. Thank you very much.